Replugging universal serial bus devices is all that you need to make them work sometimes. Welcome. We are barely set up here. There we go. Today, we are starting a new series on the emulators because it occurred to me that I literally know jack shit about emulators when I tried to make my NES emulator, and in hindsight, that emulator was bad in many ways. Anyway, we're gonna emulate something far simpler. We're gonna emulate Ben Eater's 8-bit computer. Now this is a computer that this guy, Ben Eater, has literally built on breadboards, and you can go watch his videos. He demonstrates building the actual computer, and he demonstrates running programs on it, and he demonstrates basically everything there is about it. There's a part list if you actually want to build it. We're not going to focus on that though, we're going to focus on emulating it. And we're going to be emulating it in a few different ways. In this episode, well, this part, we're going to at least try to get it to work in interpreted mode. Now, interpreted emulators are some of the easiest emulators to write because you're just pretending to be the processor even though you're not. You're interpreting. And we'll get more into that. But for now, we're gonna find some relevant data. If there's any available. What you need for an emulator. Basic information is processor type, and from there you can get everything you need about the processor. But this is not an individual processor. This is a bunch of logic gates put together. So what we need is, this is basically our processor definition here, and we need to find one thing first, and that is the instruction set. Now, I've seen the instruction set in one of his videos. I mean, if he... Maybe I'm just bad at navigating websites. Okay, now it's in the 8-bit computer category, what the fuck that means. Let's go down somewhere here. Okay, here's a bit about Ben Eater, there's his face. Navigation on this site is next to none. That's kind of bad. Now, this is problem, not part. This is problem number one you'll likely run into when creating an emulator. And that is that you will not find the specs. You won't find a piece of data that you really need. What do you do then? We are at the prime source. There's nothing really here. Control F. Make sure there is no match for instruction set. There is 5 matches for instruction. Adding more machine language instructions to the CPU.
So we've pretty much built most of our CPU, and the microcode has been programmed.
Here we go,
with
a video from him.
Instructions.
Now I'm gonna mute that because all we really need is already in frame, to my knowledge, unless he actually adds more stuff. I think he's writing actual program right there. I want to see the actual instruction table. Maybe that's... No, that's the program he wrote. Maybe it's back here at the beginning and I just... I'm an ass and I missed it. Okay, what instructions are you gonna add, Mr. Ben? Okay, so that's the current. These are our current opcodes, and he just added a story. Wow. Let's see if he's gonna add anything more. Load intermediate, jump. Okay, so that was the last instruction he finished adding before programming it into the EEPROM, which is his... he has two EEPROMs which acts as demuxers or decoders. Instruction decoders, yes. They take the instruction as the current instruction as an address plus the current cycle as a two or 3-bit binary thing, which is also added to the other bits on the address, and that's how you get this sequential thing here of 1, 2, 3, 4, 5, 6, 7, 8 steps. So it's using 4 bits of the address to show which language. He uses 4 bits of the address to denotate to the EEPROM what cycle it is on, if it's on a read, decode, fetch or write back cycle or whatever that is. I was not in the correct order. And the other 4 bits are, well, the instruction, because he only has 16. He only has space for 16 instructions here, 4 bits. So 4 bits are the actual instructions, and then the other 4 bits going to the EEPROM is the current cycle it's on. And that's how you get to do the sequential execution here. Also, would that be a decoder, or would that be a decoder and some kind of sequencer smacked together? Let's not dwell on it. Let's just emulate this thing. So I haven't even done an audio check. I'm stupid. Let's do that real quick. Yes, that's working. Let's stop that. Now, here is the data we needed. We're gonna quickly open a terminal, and we're also gonna open something Sublime Text. There we go. Oh, and here's this. Get out of my face. Not saved. Sure, save that. It's unable to save. Sure. Okay. Folder name, then Ether, CPU, and as I said, today we're gonna interpret it. Then Ether CPU interpreter. There you go. And for all of these videos, I am going to I'm gonna stick to Python because it's easy to read and understand. It's not the fastest thing, but we don't need the fastest thing in the world when what we're executing is literally 16 bits of address space. No, 16 possible address spaces, 4 bits, not 16 bits. That would be 65,350 something, whatever, referred to the Minecraft default port and add a 3 instead of a 2. 35565, there you go. Actually, that's signed. Where's that? Wait. This is why I should not be streaming videos, because I just get distracted. 16 bits integer maximum. It should be 65,000 something. 65,536. Or if it's signed, it should be... okay. Well, half of that, so 35,000. Okay. So, we have a new file. We're gonna save it as main.py because we don't really know what to do with this yet. Now we're gonna define main, because why not? Then we're gonna pass that. It's not gonna do anything. If our name is equal to main, then we're gonna run main. So when we run this module individually, it's gonna run main. When we load it, it's not gonna run main. That's good to know. But actually, we still kind of need that pass there. Let's define some data that this script can throw around and use. So we're gonna define basically just like this. We're gonna take this and more or less copy it over into... oh, why is it so big? Oh god. So we're gonna have something called instruction. Actually, that should be instruction set. Now, I'm making this a tuple for one reason, and this is just a Python thing, is that tuples are immutable. If you try to like change an index in the instruction set, it would just error out and tell you that tuples are immutable. And that's just a safety thing. So if you have like static data that you don't want to be changed, and you want to make sure of that, and if it's a list, make it a tuple instead of your, well, list. So, problem number 2. How to define your data for your script to use, or for your code to mess around with. So now you gotta actually use your brain here a bit, and you gotta figure out, okay, so we have our instructions here: operation, load A, add, subtract, store A, load, intermediate, jump, bunch of blanks, and then out and halt. You could just put that in as some sort of I mean, ideally, the instruction set should contain, for each instructions, the sub-instructions needed to get that thing done. So let's do that. So we're gonna basically replicate this line for line, and this first instruction here is gonna be our no-op, which is gonna be here. And we're gonna define that as a tuple again, just because. And inside this tuple, we will have basically what's here. Now, MICO, ROIICE, BI, AI, etc. These are all flags that Ben has defined, and I generally stands for in, O generally stands for out. So you have memory in, counter out, which takes the counter and loads it into memory. And then you have something out. I forgot how all of this works. Something in, counter enable. So there's two ways to do this. You could either emulate it at... actually, let me rephrase that. When it comes to emulation, you get this realization that you can abstract things to any level. If you want to, you could interpretly, like, run. No, you could build your emulator so that it actually replicates all of these instructions here, so that it actually does everything, and that everything is its own abstract thing. Or you could go up a couple of levels and you just abstract it all so that a no-op calls a no-op instruction, and LDA loads a LDA instruction which modifies some variables in the local object. So we're gonna go for the simple approach here, and we're not gonna define all of these signals here. We're gonna just not care about that. We're gonna analyze these signals later, determine their outcome, and then replicate it in our own code. That's what interpreting means, I think. Don't quote me on that. So our instruction set is just going to be a list linked to other lists, I guess. No. A list containing a bunch of instructions. So we're gonna have nop, LDA, add, subtract, store A, load intermediate, jump. And then we're just gonna have a bunch of null. I guess we can just do that. How many nulls? 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. And then we have out and halt. So we have our instruction set defined, but it's not actually defined because we haven't defined anything of the nop, LDA, add, sub, jump, out, whatever. So let's do that. Should I write this as a class, or should I just write it to run directly in the module? I'm gonna write it to run directly in the module, and then I move the module into a class and be done with it. Also, if you want your code to be clean, keep your screaming case variables, also known as constants, at the top of your file and define stuff underneath them and not above them. That's a good place to start. So we have our nop, which does nothing, literally. We have our LDA, which should load A, but we're just gonna make it pass, and we're just gonna do this for all of this. Nop LDA. Nop LDA. Add. Subtract, store A, load A, no, load intermediate, jump, null, out, halt. There we go, we've printed so many things we need. Load intermediates. We have our jump. We have our null, which I'm actually gonna right now just do this. Raise exceptino. Exceptino. Okay. Exception. Raise exception, null, instruction executed. Exetered. What the f... Can I spell today? Dank. Very dank. That was our null. After our null we had our out and our halt. Now, all of these currently do jack shit. And if you really want to be clean about it, you could do a new file and you could save it as instruction set. And you could take your definitions, take them from there, throw them in here. This should also be in here, but it will... Ooh, can it be at the top? Something tells me Python sequential loading will not allow this to be at the top. But then from your original file... Also, you probably can't see jack shit of this. Here you go. Zoom in a bit. So we're gonna import, if you want to be verbose, so Python understands you, you could do from dot import. I don't think that's supported anymore in Python 3. So there's a small chance that this will try to load a global module called instruction set, but it probably will not exist, so it's just going to load our file. Don't quote me on that. From instruction set, import instruction set. Wow. So let's pop back into our terminal and let's run this for the first time and see what happens. Probably nothing, but that's what we want. At least we don't want it to crash. And we get an error. Name nop is not defined. So yes, I was right. This is going to need to be at the bottom of the file. And that's why you should have a separate file for your constants. And then you can import that constants file into whatever no wait. This is because it depends on stuff that's above it, so... Who cares? It's all a matter of taste anyway. Now when we run it, there we go, it does jack shit. Just as we want it to. We might as well add a comment here saying intended behavior. Just so we're clear to ourselves. Now what? Now what? Problem number 3 of writing an emulator. You need to get some kind of test program to test your thing against. So I'm gonna go to the end of this video. Where we have a load intermediate, store A, load intermediate, add out jump to 3, which adds 15 out jump, add 15 out jump. So okay, just gonna add address 15, load intermediate 3, store accumulator to address 15, load intermediate 0, add from address 15, so we add 3, so we get 3, we output that, we get 3, we jump to, so we just output the multiples of 3. Okay, so that's what this program right here does. Let's put it in somewhere, preferably in its own file. Do we know? I think we're gonna have to, given that instructions are 4 bits in length. Can't really be well, it can be defined, well, represented as a hex file, but it's, then you have to do a bunch of byte splitting and all that stuff. So we're just gonna have a file here, and we're gonna call this program.py, and then we're gonna from program import no. Our program is gonna be no. This ain't gonna, we're gonna have to rename this file. We're gonna rename this and call it RAM, because the program resides in RAM. Oh, program RAM. Oh, ha, that was unintentional, but that worked out. Anyway, we're gonna do that from RAM, import RAM. RAM is gonna be a list, because this is actually gonna be changeable. Now we want some kind of default initialization. Actually not, because this is, we're trying to emulate a real world thing. Sorry, I probably deafened you all there. Probably broke the microphone in process too. What was I saying? Well, it's lost, whatever. Yes, since we're emulating a real thing, we're gonna have to scramble the RAM before we turn it on. So, from random import random, thank you. Random. And I have actually forgot how random works. Python, no, not a random, random, integer. Okay. Well, okay, that works, I guess. We'll just do this, import random. So, let's run this again. And there's our RAM. It's scrambled, it's going to be different every time. That's not the program. There you go. So the RAM is scrambled. We might want to disable that for debugging purposes, so we get a clean RAM. So let's do the pinnacle of debugging here and do so, and comment out one of them and just do that. There we go. Now we got empty RAM. Completely empty. And we can put our program in there. So RAM. Actually, I think I'm gonna do it the reverse way around. RAM equals something that we wanted to. Now this RAM is 8-bit capable. I think. The RAM can store 8 bits, yes, but we only have 16 address spaces to muck around with. So that's why doing random to 255 instead of 16, I guess. Usually when it comes to RAM and computers, the address space is much larger than the bit space in the RAM. So for example, you have the 6502. It has 16 bits of address space, and each address can store 8 bytes. Here it's different. Well, here it's the other way around. Here you have 4 bits of address space and 8 bits of actual memory space. Memory bits. Anyway, we are gonna put in our program, which we're gonna test with, which we're gonna get from here. So we have load intermediate. 0, 1, 2, 3, 4, 5. Oh. Instruction number 5. Oh yes, that needs I'm gonna go back and look at his execution table here that he had. Oh, this isn't. There it was. Ah, no. There we go. 5 minutes, 58 seconds if you want that screen. Anyway, what I want to look at here is the load intermediate instruction. I want to see if it actually wait, what? Okay, that makes sense. As I said before, no, not as I said before, this is in a different case. We do have 4 bits of address space here. We do have, well, 4 of the bits. Here's the thing. Where does the last 4 bits go? That might seem a bit random, but each instruction is stored in RAM, which is 8 bits wide. So this ROM gets, well, I guess the lower 4 bits. But what happens to the top 4 bits? I'm guessing he just drops the bits. I think I remember that he does that somewhere in some video. So, our operands are baked into our opcodes. 4 bits of the opcode is the actual opcode, and the last 4 bits are potential operands. Like 3, 15, 0, 15, nothing, and then 3, I think. So we're gonna have to bake that into the numbers. This table here, right here, we could use that and just copy it, because Python will handle our binary definitions. 0b, is that how I, or is it b0? It must be 0b. So, first RAM is 01010011. Next one is 0100 111. I mistyped. Somehow an extra 0 snuck in there. We have, what do we have next? We have 0101 because it's LDI. 0101. Oh, we load 0, so a lot of zeros. What we load next? Into red. Now we have add. which is 00 what? 10. We're gonna add from the topmost address, which we stored at 3.2 before. And we are going to do out, which is 0b 1110, and it doesn't have an operand, so we're just gonna leave that as 0. Zero one one zero 0011. So 0110 is our jump, and 0011 is our address. You see how these are like baked together? That's our program right there. That's gonna count the multiples of 3 when we're done with this. So, back to doing some testing. There we go. Our bytes, whatever they appear to be 83, 79, 80, 47, 224, and 99 are all loaded at the beginning of RAM, and then we have a bunch of zeros after, which we appended in a while loop. And we make sure, yes, we have 16 bytes of RAM there. Actually, wait, that's probably useful information to have. So let's do print dash dash RAM dash dash. There we go. Nice overview. And it doesn't format properly. And this won't work either, will it? That does work. Oh, it's because print is not a function in Python 2. It's a syntax thing. Oh, there you go. 16 bytes of RAM with our stuff in there. Now we just gotta define what all of these instructions do. So let's analyze the actual computer right here in its coppery gloriness. And actually, let's not. Let's just assume things. Let's go by the name and let's use intuition. And where intuition fails us, we're gonna revert back to doing some good old-fashioned research. So, back in our main here, what do we need? We're gonna need a program counter. We're gonna need an accumulator. We are gonna need so I guess the accumulator is the sum. Wait, does he have a STB, store B? I don't think so. Okay, so AI is A registering, BI is B registering. Okay, so let's use that on this chart here and see what the LDA, which is load accumulator traditionally, and let's see what that does. So MICO, no idea. ROIICE, no idea. Doesn't matter. It's the same for all. And then we get to the interesting stuff. Load A, IO. What was IO? Instruction register out. Oh yeah, that's the instruction decoder. Oh yeah, here we see that 4-bit thing, that 4-bit split thing. Your program counter indexes to the RAM sends the address out to the bus sends it to the instruction decoder puts some of the bits that they read from RAM back out onto the bus when you enable the register out, and it also enables this piece here, these 4 bits, to actually be executed. So let's go back and decode that. So we have instruction register out, memory in, R, RAM in, RAM out, A in. How do you load stuff into the B register? I mean, adding and subtracting uses it, but EO here. There we have 2 EOs on the add and subtract. Yeah, makes sense. But that's working on the B register as well. How do you access the B register? Oh wait, the B registers is not really a register. It is a register, but it's not a... Currently, with the current instructions that this computer have, this computer does not support reading out the B register, even though it's fully capable to. Yeah, both A and B register can communicate back to the bus, and the output from the ELU. I wonder if that gets put back into the accumulator. So the B register is basically an intermediate shadow register. This processor uses. It takes the instruction, whatever it's going to do, either it's add or subtract, and that's going to be referring to an address, probably. So what that does is that it reads the instruction, it fetches that address in RAM, puts it into B, and then it adds or subtracts it with the contents in A, and then the output that you get back hopefully gets put back into A. We can check that here, subtract and add. So we have enable out for the ALU for add and subtract, AI, which was A register in. Oh, and here's for the subtract, it actually turns on the subtract flag as well, so you get the actual subtraction. So yes, it does load it back into A again. So we could define our B register here, but it's not really needed. However, if you want to stay true and support weird functionality like overflows and weird program flows, and like for example, if the B if you try to add with the address that's outside of RAM, maybe that does something fun. So we're gonna have the B register in here. We're not gonna use it that much, but we're gonna have it. And what are we gonna have more? Not much more, to be honest. Also, all of this should probably define. Actually, no, it could be defined here. Actually, no, it can't, because it needs to be used in the instruction set. I'm gonna take all of this, put it back in here. God, that's horrible. Anyways, that's kind of a nice separation, I guess. Because now we got our instructions that the emulated CPU is going to use at the top, and then we got our constants, and then we're going to have our internal helper functions, I guess. So let's start jotting down what all these do. So what's almost always going to happen, if not all, actually it does happen always, because if you check this table here, you have counter enable on every clock, or well, on every instruction. So it's gonna increment the program counter. Let's just say that. So should we do that in main? Yeah, we'll do it in main for now. Program counter equals program counter. You want to do something like that, make sure it wraps around. So program counter is program counter plus 1 modulo 16. That just to make sure we wrap around back to 0, if that's any need. Now that's done after here. Counter enable is done after we do memory in, so we're gonna have to actually read the instruction before we do the program counter stuff. So I guess we're gonna need a instruction called read RAM address return RAM. Now this might seem unnecessary, but it keeps flexibilities in the mix. You can flex this around and make it into something different without fucking it up too much, is what I'm trying to say. So we're gonna read RAM at the program counter, and from that we're gonna get a opcode. Now we could print this opcode, and it would literally do jack shit, I think. It would just print out, okay. PC reference before assignment. because it thinks it's a local. I shouldn't have done this in a module. I should have done this in a class. So we get 83, which is the first byte. So it read the first byte from RAM. Woohoo. Good on us, I guess. That's not really gonna do anything. So let's use that opcode and, as they say, shop the, I think it's top 4 bits off. I'm gonna call that data. I'm gonna have the opcode be data, but we wanna shop some bits over there. So how do we do that in Python? Google. Python bitwise bit manipulation. Yes, there you go. Bit manipulation, Python wiki. I want to. I mean, I believe I can just AND it. Just do that. Data and 0b. I want the first. Where's that last? I think that's the last. Whatever. So we have opcode and arguments. Let's try and print data. Let's print opcode. Let's print arg. Yes. Opcode 80. Argument 3. Opcode 80 is a load intermediates. The first instruction we have is a load intermediates, which is going to load the number 3 according to the video. Well, if it was here. It's not. But there it is, 80 and 83. Now, excuse me, I'll be back. Hello. Welcome back. Or I should say, I am back. And where we left off, we did some debug printing, which we have verified is now working. That's how you test code, by the way. Now we just gotta... Well, we have our opcode. We basically go instruction set. Not with the opcode. Hold on. Food is soon here. And I realize we can't really define that instruction set. Yes, say that. We're gonna convert this instruction set to a dictionary. There we go. Let's do some Sublime Magic and do 0B 1 2 3 4 1 2 3 4. There we go. We're running again. We're just gonna have to do these definitions. So let's go back. I'm gonna try to do that so it's easier. Actually, since this is just equivalent of the number we got here, we could theoretically bit shift it to get our index. So I'm gonna switch this back to and we're gonna do so taking that, bit shifting it, should give us four bits up, 4 bits down, who knows? We're just gonna do a print to find out, because that's how we are most efficient. We aim for a number that's smaller than 80, which that is not. Five. So instruction 5, 0, 1, 2, 3, 4, 5, LDI. And we wanted what did we want? We wanted, I think we wanted the LDI. Yes. So we're gonna execute that, and we're gonna send the arg with it, and that's all. Literally, that's all we need to do to actually execute our cycle. Now we're gonna need to modify all of these, so let's do that quickly to accept the argument. There we go. So, load A, it's gonna take an address and load that into the accumulator. So, accumulator equals RAM with the address of argument. Yeah. Add is gonna be B equals RAM arg, and then we're gonna have A equals A plus B, and in subtract here you could do this and do that, but you're repeating yourself. If you're writing code, don't repeat yourself. So what we're gonna do is in the subtract function, we're gonna run the add function. Wait, what? Yes, this just we're gonna run the subtract runs the add with a negative argument. Oh wait. Hold on. Food has been delivered, and since this is the address, we're gonna have to do a repeat of ourselves, which kind of sucks, but hey. So, store A. That's gonna take A and store it to memory. So RAM with the argument, which is our address, is going to be A. Load I, load the intermediate, is going to load into the accumulator, and since it's intermediate, it's just going to load the argument. Now jump is going to set the program counter to the argument, I assume, and out is going to do a print with the RAM address, with the RAM contents of that address we get. And then halt is, we could raise exception here. Raise exception completed. So we have defined our instruction set theoretically, and it's not really that much. Let's see if it even compiles. It compiles and runs. After each instruction, I'm gonna print the RAM. And since nothing happened, and since the first instruction we ran is a load, we're gonna print A, and we're gonna print B, and we're gonna print the program counter as well. Actually, that should... No, that should be here. Or should it? A is 0, B is 0, PC is 0 after our first instruction. Now, if you want to be verbose, you could do this. Set all, yes. Go on that. Yeah, copy of that. Something happened there. I have no idea what the fuck happened. Oh, because one of them was... There, now we print every instruction we run. So we ran the LDI instruction, load intermediate. It should have put A to the arg. Now, it occurs to me that A, in all of these circumstances, are probably a local variable. So global A, and B. Global A and B, global A, and here we need a global PC counter, and that's it. There we go. Now our A contains a free C. So while true run main, we're just going to continuously execute, and it's going to do something. Well, it's executing, it's not crashing. Let's scroll back up to the top again if we can. Probably not. So let's import from, actually just import time. Time.sleep. So, we load I, we store A, we load I, we add, we out, we jump, we out, we jump, we out, we jump. Okay, so just from that, I can tell you that our program counter jump should be -1, or it's because I should do this before I execute the instruction, because that's how the actual CPU does it. Okay, let's do that. There we go, 6, 9, 12, 15, 18, 21, 24, 30, 33, 42, 48, 51, 50, 60, 69, 78, 80, 90, 900, and yes, as you can see, it's running. We have interpreted CPU running in Python. And it's running a very simple program utilizing literally no RAM. And it's now up to 300, so we're not actually compliant with Ben Eater's CPU. Ben Eater's CPU would have rolled over and started again instead of keep going to 480 something. So yes. That is an interpreted emulator. Next time we're gonna have a look at a just-in-time intermediate language emulator. Yes, if you're interested in what that means, just use Google, use Wikipedia. have all these resources at your fingertips, just use them. Anyway, that's been it. I'm probably gonna run some more programs on this, and I'm probably gonna fix it at the beginning of next episode. And yes, it's here, it runs stuff. The only problem right now is that the program counter, the A register and the B register, essentially all external things that's not in RAM, can overflow because they don't have a hard cap to 8 bits. So essentially I have to do a check at each one of these where I assign A or B. Or I could write some help functions that would be called read A and write A, and that would do the overflowing to 4 bits for me. But yes, that is it. How does it out though? Out, and then it tries to print that. Maybe out just prints out the accumulator. I'm gonna assume that's it. And out 39, out 36, out 33. Yes, this is all very nice and stuff. So let's be less verbose so you can see what happens. Yes, I know that's weird, but there you go. We're now executing instructions, and every so often we get a number in there, and that's our output. So load I, store A, load I, add out 3, jump add out 6, jump add out 9, jump add out 12, jump add out 15. Yeah, it just works. So I'm gonna be back next time. Bye bye.